In 1980, a Russian-German mathematician named Yuri Manin introduced an idea that could revolutionize the modern world. After writing his paper, Computable and Uncomputable, Yuri inspired many mathematicians, programmers, and physicists to chase the idea of quantum computing. Only a year later, well-known names such as Richard Feynman and Paul Benioff would rise to the challenge of theorizing the first quantum computers. Fast forward to the 90s and 2000s, and we have many leaps in quantum computing. Inventions such as Shor's algorithm, which can theoretically crack most cryptography used today, to D-Wave, the first company dedicated to quantum computing. But what exactly is quantum computing? In traditional computing, a binary system using transistors are either on, 1, or off, 0. These numerical values are referred to as bits. A bit can only be 1 or 0, but not both. To increase the computing power of traditional computers, you must add more transistors. This has led to processors that contain billions of transistors. Theoretically, we are approaching the limits of how many transistors we can fit into a small space. Quantum computers could help solve this problem. Quantum computers use qubits, or quantum bits. Unlike traditional bits, qubits can exist as both a 1 or 0 at the same time until observed. This is known as superposition. So how does superposition enable quantum computers to be more powerful? The easiest way to explain the difference in power between a traditional computer and a quantum computer is by looking at how information is computed in both systems. In a 4-bit traditional computer, you will end up with 16 possible combinations of bits. Only one of these combinations can be used at a time, meaning a classical computer would need to repeat itself 16 times in order to get the correct combination. A 4-qubit system can be all 16 combinations at the same time, and the more qubits you add, the more powerful this system gets. For example, a 500-qubit system can hold more combinations than there are atoms in the universe. This is due to the equation 2 to the power of n, where n represents the number of qubits in the system. In other words, you will see exponential growth in computing power as you add qubits to the system. The applications of quantum computers could change the face of humanity as we know it. Quantum computers may one day have the ability to create advanced artificial intelligence, solve incredible health problems, crack the most sophisticated cryptography, run complex simulations, and quickly sort through huge amounts of data. However, powerful quantum computers that can do these things are still out of reach. This is due to the problem of decoherence. Qubits are susceptible to interference from light, other particles, temperature changes, and many other factors. This makes data from quantum computers faulty and unreliable. Currently, the best method in use to curb decoherence is to use superconductors cooled to nearly negative 273 degrees Celsius, also known as absolute zero. So don't expect to be using a quantum computer at home anytime soon. The world of quantum computing is both strange and exciting. With new advancements being made every day, it's only a matter of time until we start seeing the benefits of this technology in everyday life. Whether it's from advances in medicine to advanced artificial intelligence, the benefits of using quantum computing will have lasting effects on humanity.